Benedict will speak of social choice in infinite societies, and these two last talks will be on, well, in English, I guess, at least this one, and and on social choice theory or computational aspects in social choice theory. Thank you.
Thanks, Alberto. Okay, so I suppose I'm going to be talking about computation, but also non-computation or non-computability. I'm going to start out just giving the basic sort of framework here for social choice theory. And we'll start with Condorcet, of course, and the famous Condorcet paradox. So this is a paradox concerning majority rule, which is kind of obvious way of making decisions. You have a group of people, let's call them voters, and they want to make some kind of choice out of some set of alternatives. So majority rule just says, okay, if we have alternatives X and Y, then if a majority prefer X to Y, then so should the society. This seems kind of reasonable. But then here's a scenario where this doesn't work. So suppose we have some voter A that prefers X to Y and Y to Z, and voter B who prefers Y to Z and Z to X, and then voter C who prefers Z to X and X to Y. So fortunately there are only three, so it doesn't get too complicated. But then we see a majority prefer X to Y, so voter A and voter C, and a majority prefer Y to Z, A and B, and a majority also prefer Z to X, and we see now there's going to be some kind of problem because we want to choose an alternative out of X, Y, and Z. X is preferred to Y by the society, by the basis of this rule. So, and Y is preferred to Z, and we think that preference is some kind of transitive relation. So X should be preferable to Z. But in fact, Z is preferred to X by this majority rule. So we have some kind of contradiction, at least a contradiction with the notion of preference, right? We think that preference is a notion that should be transitive. If I prefer X to Y and I prefer Y to Z, then I should prefer X to Z. But then notice that these voters individually are not violating that condition. Their preferences can be transitive. It's just that the rule is inducing a social preference ordering that is non-transitive. So that's the Condorcet paradox. So even if the voters are individually rational, this majority rule can lead to socially irrational outcomes. So an obvious suggestion here is, well, we need to impose some conditions on what our aggregation functions should be if we're going to rule out scenarios like this. So for example, we want our social preference ordering to be transitive. And we also want that any two alternatives should be comparable. We might not have a preference between them, but they should be comparable. They should both appear in the ordering. And yeah, ties should be permitted to express indifference. And this leads to a certain notion of ordering called a weak order. You see it called various different things in the literature, but I'm going to stick with this term. Okay, so here's just the definition of a weak order, but just think of it like this. It's like a linear order that allows ties. That's all that's really necessary. Okay. So some notation. I'm afraid we're going to have some notation in this talk. So we have this x less than with a subscript, with a squiggle underneath. Y just means x is at least as good an alternative as y. Maybe more, or maybe they're tied. And then the strict less than just means that x is strictly preferred to y in this order. Wherever this order comes from, it might come from a voter, it might come from the social ordering. And then we also have this notion of equivalence. X is equivalent to y, just in case x is at least as good as y, and y is at least as good as x. And then we set this capital W to be just the set of all weak orderings on some set of alternatives. So we have these alternatives. These could be economic policies, or perhaps candidates in some hiring committee, whatever it is. W is just the set of all of these weak orders. Right? So they're like the possible ways we could order these alternatives. Okay, so let's talk about societies. So a society in this framework of Kenneth Arrow is something like the following. So we have a set of voters, and typically we're going to think of these as individual people, agents, but they can be other things too. We have a finite set of alternatives. So again, these could be candidates in an election, they could be economic policies, they could be candidates for a job, all these kinds of things. And then W will be just the set of all weak orders on X. And then we have this set A, which I'll explain more about later, of coalitions of voters. And we can think of this as being, to begin with, just any set of voters can be a coalition. But typically we'll think of these as being perhaps economic groups like classes, or people affiliated with certain political parties. In general, we're going to think of any set of voters as being a coalition, at least to begin with. Okay, and then we have this set F of profiles, possible voting scenarios. So what's a voting scenario? Well, it's like an election. We have these voters, and in different scenarios, they might have different preferences. Well, in this election, I prefer candidate X to Y, but in some other election, it's a different time, it's a different context. Maybe I prefer Y to X. So a profile is just a function from voters to weak orders, right? It just says, okay, given voter number one's preference is this ordering. And then in Arrow's original setting, we have this condition called unrestricted domain or universal domain. It just says, well, the coalitions are just all of the possible sets of voters, and the profiles are just all of those functions, all of those possible ways that people could have preferences, all of the logically conceivable ones. Okay, so as I said, this is called the unrestricted domain condition. And then a social welfare function is a function that maps profiles to weak orders. So you can think of it intuitively as, say, in this electoral context, the social welfare function is going to take people's votes, where we think of a vote as preference ordering, and it outputs another preference ordering. So it takes in all of the preferences of that society at that election, that profile, and produces a social ordering. So something in W. And Arrow, in trying to analyze problems like the Condorcet paradox and trying to lay down these conditions that would guarantee that we had fair and consistent ways of making these social decisions, set down a number of axioms. So the first one is kind of intuitive. It's called unanimity, or the Pareto condition. It just says, well, if everybody in the society, all voters, prefers alternative X to alternative Y, then so should the society, so should the social welfare function. This is pretty intuitive. The second condition, independence of irrelevant alternatives, which mostly I'm just going to call independence, is a bit more complicated and a bit more controversial. So roughly the idea is, if we have two profiles, call them F and G, so it may be different elections, and if they agree on two alternatives, call them X and Y, then the outputs of the social welfare function for those two elections should also agree. So if everyone in profile F has some particular ordering of X and Y, and they have, person by person, the same ordering of X and Y in this profile G, then the output should be the same in both cases. Because it shouldn't matter, is Arrow's idea, what we think about some third alternative, Z. What matters is the relative position in our orderings of X and Y. So if I prefer X to Y, in some election, and Alberto prefers y to x, and I prefer z to both alternatives, and so does Alberto in the first scenario. But in the second scenario, perhaps we both disprefer z and put x and y first. The social welfare function should in both scenarios output a weak ordering that is the same with respect to x and y. So if it puts x before y in the first scenario, it should put x before y in the second one as well. And then finally, non-dictatoriality. This is also relatively intuitive. The idea is just there shouldn't be some one individual person in the society whose preferences are always carried out by the social welfare function. So, it shouldn't be the case that if I prefer X to Y in some election, the social welfare function does. In all cases, it shouldn't be that I always get my way, or anybody. No one should always get their way. And on the basis of these conditions, Arrow proved this famous impossibility theorem. So suppose we have a society which satisfies unrestricted domain, and there's a finite set of voters. Seems pretty natural. We could be voting on something in here right now. It seems like a reasonable notion of society. And suppose that there are at least 3 alternatives. It only works then. Of course, if you only have 2 alternatives, then majority rule will work just fine, because we're not going to get this problem of non-transitivity, because we only have 2 alternatives. So if those conditions are satisfied, then there's just not going to be any social welfare function that satisfies unanimity and independence and non-dictatoriality. The conditions are inconsistent. So here's a quote from a political scientist, Riker, from 1982. And this is not exactly a representative quote of the reaction to Arrow's theorem. It's maybe at the extreme end, but nonetheless, it does give you a flavor of what people thought the upshot at least might be. So Riker says, the main thrust of Arrow's theorem and all the associated literature is that there's an unresolvable tension between logicality and fairness. Independent choice requires concentration of power in sharp conflict with democratic ideals. So there's this idea that we can't have both democracy, meaning populist democracy, and consistency and transitivity. But can we? Maybe. Maybe if we have infinitely many voters, we can. So infinite societies offer a kind of escape. I'm going to be a bit guarded about exactly what kind of escape they offer. So in 1970, Peter Fishburne proved this very nice theorem, this possibility theorem. He said, well, suppose you've got a society that satisfies unrestricted domain, and suppose you've got infinitely many voters. And you also have, 3 or more alternatives. Then there is a social welfare function that satisfies unanimity and independence and non-dictatoriality. So this seems great if you care about infinite societies. I mean, it doesn't seem like this is going to be directly applicable to a lot of everyday electoral scenarios, or, usually if you're hiring somebody, the hiring committee is probably going to be finitely many people. But there are maybe some scenarios where this is interesting. I'm just going to mention 2 basic qualms about this escape route. The first one is obviously, are infinite societies realistic in any way? Are they useful as some kind of idealization or abstraction of a political or economic situation? Are they helpful to people in the social sciences as some kind of modeling tool, or as some way of understanding normative questions, for example, about societies which extend into the future? And then secondly, okay, Fishburne's possibility theorem says, yes, you get this social welfare function. You can satisfy all of these conditions simultaneously, but how do we do it? Does it do it in a way that's actually at all useful? So I'm going to start with the first. So I'm going to present 3 different models on which infinite societies can potentially be useful. The first is just this notion of a continuous society or a continuous economy. So economists sometimes work with models where you have a continuum of agents. And the idea here is that we're really treating this as a kind of limit case of just having more and more agents. This has typically been applied not really so much primarily in the social choice context, although there is work on this, but more to do with notions of economies related to game theory, etc. So, we set the set of voters to be, say, a set of real numbers, or, you can always think when we talk about the voters being real numbers or being natural numbers or something, we're not necessarily talking about actual voters being those things, but those things being labels. So just as we're all labeled perhaps by our social security numbers or by our university ID number, we have some kind of convenient labeling system that allows us to differentiate and enumerate voters in our collection V. So prima facie, this doesn't seem a great fit for the arrow-style social choice theory, in which we really treat this set of voters discretely rather than continuously. I won't say too much about this. But if you have a kind of continuous treatment of V, in fact, you recover Arrow's theorem or something rather like it. Okay, so a second one is societies that are infinite through time. So in population ethics and intergenerational social choice theory, we might think about scenarios where new voters keep being born. And if the universe extends far enough and we want to consider a wide enough notion of society or what a voter might be, they might not be from Earth, they might be somewhere outside our light cone. Nonetheless, we might want to consider them as having views about how things should be, and people do. And in these kinds of scenarios, we typically don't assume that there are a continuum of voters, but just that there are countably infinitely many individuals. So as many individuals as there are integers, right? Whole numbers, natural numbers. It's not immediately clear whether social decision-making of the sort described by Arrow is applicable to such scenarios. There is a literature on it, but I wouldn't commit to the plausibility of this kind of thought experiment. I mean, for one thing, that if we want to actually carry out some kind of decision, even if we have some way of taking into account the views of future people, perhaps we compute what we think they might want, still any kind of action will have to be taken before they can really make their views known. And then finally, in some ways perhaps most plausibly, is a third type of infinite society. So it's one where there's only finitely many agents, just thinking about a more normal electoral society. So we only have finitely many, say, human beings making decisions, but they're conditioning their preferences on possible states of the world. So they're saying, well, if things are like this, then these are my preferences. But if things are like that, then my preferences are like this. And then it's easy to get infinitely many, quote unquote, voters. So each voter consists of a pair of an agent and a state. And when the set of states is infinite, so will be the set of voters. Okay, so that's three types of infinite society that might be of interest, either for modeling or for kind of more normative purposes. So now turning to the second question, what kind of social welfare functions do we get out of this Fishburne possibility theorem? So normally, when we think of social welfare functions, we think of them as applications of rules, right? So the function is a kind of a mathematical operation. It's mapping one thing to another. But how does it do it? Well, it does it through a rule. And this is kind of naturally conceived also as an algorithm. So if you think of majority rule, what do? Well, you just count up how many people want option A versus option B. And in fact, Sen refers to the more general class of functions that include social welfare functions as collective choice rules. The very use of this terminology demonstrates the way in which these things are being thought about as rules and thus, in some sense, as algorithms. And here we have a problem because Fishburne's proof doesn't produce something that looks like a rule or like it could be operationalized by a rule. It uses these very non-constructive methods, in fact. And this suggests a kind of obvious worry. Well, Fishburne shows that there are, mathematically speaking, these non-dictatorial social welfare functions, but do any of them correspond to rules? Are there any that we could actually even potentially use? So as I've already said, in this context, a natural way of understanding the notion of a rule is as an algorithm or as a computable function. Okay, so with all of this sitting there, we can go sort of more to the mathematics and to the modeling of all of this. So I first need to talk a bit about this notion of a decisive coalition. And this was introduced by Arrow, and you can think of it as a kind of generalization of the notion of a dictator. So a decisive coalition is one that always gets its way. And of course, the set of all voters is a decisive coalition by the unanimity axiom. So yeah, just some more notation, given some coalition, we have this square bracket C after the profile F to mean everyone in that coalition prefers X to Y, possibly non-strictly. And then a coalition C is sigma decisive, where sigma is a social welfare function, just in case for any profile F and any pair of alternatives X and Y, if everyone in the coalition prefers X to Y strictly, then so does the social welfare function. Right? So it's just a straightforward generalization of the notion of a dictator or of unanimity. And this notion was used by Kerman and Sondermann in the 70s to basically reprove Arrow's theorem on the basis of this analysis of these decisive coalitions. So here's the theorem they proved. So suppose we have a society that's going to satisfy our usual conditions, unrestricted domain, it's got at least 3 alternatives, and we have a social welfare function, which we assume satisfies unanimity and satisfies independence. Then there exists an ultrafilter on the set of coalitions consisting of exactly those coalitions which are sigma decisive. So you might say, okay, but what's an ultrafilter? Well, an ultrafilter is a kind of notion of a collection of large sets. So anything small, anything finite will be in one partition, not in the ultrafilter. Anything big will be in the ultrafilter. One way of thinking about this. And the ultrafilter will be principal just in case the social welfare function is dictatorial. So a principal ultrafilter is one generated by a single element. So a coalition will be in the ultrafilter just in case it contains that element, which is, of course, the dictator. Now, this theorem applies not just to finite sets of voters, but also to infinite sets of voters. And you can prove this in the standard formal theory for formalizing pretty much all of mathematics, Zermelo-Frankel set theory, ZF. And this shows, by an argument that I won't give, that Fishburne's possibility theorem is not provable within that system. It's genuinely non-constructive in the sense that it goes outside this system because it implies the existence of what's called a non-principal ultrafilter, one that's not generated by a single element. Okay, so this gives us a kind of starting point. It says, well, Fishburne's possibility theorem, it seems like it's not going to give us anything computable, anything tractable. So here are some questions that I will attempt to provide more fine-grained answers to. So the first is, are there non-dictatorial social welfare functions that do correspond to rules, ones that we can compute? This was previously examined in the 80s by Alan Lewis and in the 90s by Reju Mahara. And in general, the answer is no, but the answer will be a bit more subtle than this. So here's the more subtle version. how non-computable are these functions, and thus are there electoral scenarios or infinite societies where it might make sense to think about non-computable but not very non-computable social welfare functions. Perhaps some of these three scenarios that I proposed at the beginning might be more amenable to this than others. And then the second question, which looks like it's a very different question, but in fact is intimately related to the first, is, are non-constructive axioms, like the axiom of choice, necessary to prove Fishburne's possibility theorem? And again, the answer is going to be yes, but also no. So I hope to provide something more satisfying towards the end of the talk. But roughly the answer is going to be non-constructive principles are necessary, where by non-constructive I now mean non-computable, but these principles are much less non-constructive than one might imagine. So you're going to get non-computable sets, but not that high up in the hierarchy of non-computable sets. Okay, so having done all the setup, we now proceed to talk about some logic. So I will try to just give a sort of sketch of how this goes. So just some sort of background here. So the framework I'm going to be looking at is called reverse mathematics. And the idea of reverse mathematics is to say, well, we've got all these mathematical theorems, like, for example, Fishburne's possibility theorem or the Kerman-Sondermann theorem. What do we need to prove that? What's actually necessary? And this turns out to be intimately connected to the question of what kind of solutions are there to the problems posed by theorems. Right? So a problem might be something like an infinite society, and a solution would be a non-dictatorial social welfare function for that society. So what do we mean for an axiom to be necessary for proving a theorem? And one obvious and basic idea is just, well, if the theorem implies the axiom, if you can prove the axiom from the theorem, hence the reverse part of reverse mathematics. And reverse mathematics is just a subfield of mathematical logic connected to computability theory and proof theory that's really dedicated to answering questions of this form. And there have been hundreds and hundreds of ordinary mathematical theorems analyzed in this way using this framework. So in working with this, we're going to be able to place things like the Fishburne possibility theorem, the Kerman-Sondermann theorem, Arrow's theorem, into this well-understood universe of results and say exactly where in this hierarchy of principles these things work out to be. So the formal setting is a language called L2 of second-order arithmetic and axiom systems called systems of second-order arithmetic. So second-order arithmetic is a language in which we can talk about natural numbers, 0, 1, 2, 3, etc., and addition, multiplication, less than, but also about sets of natural numbers. So the set of primes, or the set of odd numbers, set of even numbers, the set of numbers which are the indexes of Turing machines that halt when given their own code as an input, this kind of thing. Okay, so it's a quite expressive language. It's a two-sorted language in the signature, and then the structures are like this. I won't belabor this too much, but roughly the idea is that we have this two-part domain, one part with numbers in and one part with sets of numbers, more or less. And using this framework, you can formalize a lot of analysis, countable algebra, topology of complete separable metric spaces, infinitary combinatorics like Ramsey's theorem, mathematical logic, and so on and so forth. And now also, it turns out, social choice theory. Okay, and then the hierarchy that I talked about of these subsystems of second-order arithmetic consists of systems that extend this basic system called RCA 0. And the way to think about RCA 0 is, well, we've got some arithmetic. You can do addition, multiplication. You can do a bit of induction. But it also posits the existence of computable sets of natural numbers. So if you have a set of natural numbers that can be computed by a Turing machine, computed by an algorithm, then RCA 0 can prove that set exists. And then we extend that with this increasing list of set existence principles that are stronger and stronger. I'm only going to talk about one of them, so don't worry about what the others are. This one, ACA 0. Okay, so yeah, in case you're interested, these are the axioms for RCA 0. I couldn't even really fit them all on because number 1 is kind of long, but the sketch I gave you before is all that you really need, that we have some arithmetic, some induction, and comprehension for computable sets. So how does reverse mathematics work? Well, it works like this. You formalize a mathematical theorem as a statement in this language of second order arithmetic. So if I want to prove an equivalence, say, between arithmetical comprehension and the Bolzano-Weierstrass theorem, that every convergent sequence of real numbers has, every bounded sequence of real numbers has a convergent subsequence, I have to find a way to formalize the notion of real number and sequence and convergence. And once I've done all that, then I can express it as a statement in this formal language. And then the work starts. Then you prove it. You prove that statement in some subsystem of second order arithmetic, in my example, ACA 0. And then you go back, right? You do the reversal. You add your formal statement to the base theory, and you prove the axioms of the theory that you're proving it equivalent to. Right? So in my example, you've formalized the Bolzano-Weierstrass theorem. You prove the formalized version of this theorem in ACA 0, and then you do the reversal by taking your formalized version of the Bolzano-Weierstrass theorem, adding it as an axiom to the axioms of RCA 0, and proving arithmetical comprehension. And there's a kind of deep connection between reverse mathematics and computability theory. In particular, this idea called recursive counterexample. So recursive counterexample is when you have some theorem. It's asking a question, is there, say, given us an infinite society, is there a non-dictatorial social welfare function? And if it's the case that you can construct a society that's computable, that has no computable solutions, that's a recursive counterexample, because it shows that the theorem is false when you interpret its set quantifiers as ranging over the computable sets. So when we do these reversals from theorems to axioms, very often the way it works is that we will do exactly this, but within RCA 0. So we formalize this construction of a recursive counterexample. So you construct the recursive counterexample as a set in RCA 0. So it's as a computable instance of your theorem. And then the theorem says, well, given, say, any infinite society, there exists a non-dictatorial social welfare function for that society. But then it turns out that that thing is very complicated, and that allows you to prove this set existence axiom, for example, arithmetical comprehension. Okay, so what is this arithmetical comprehension axiom? Well, it just says that every set definable by a formula in the language of first order arithmetic exists. This might seem kind of innocuous, but in fact, you can define a lot of stuff in this way. So we can define limits of convergent sequences of real numbers, paths through infinite but finitely branching trees, so Koenig's lemma, the sets of codes of Turing machines that halt on all inputs. So you can see, at least with this last one, that this is an axiom that allows us to prove the existence of non-computable sets, to go beyond the computable. which RCA 0 doesn't do. RCA 0 is computably true. All of its axioms can be made true when we just look at the computable sets. But ACA 0 is not like this. Okay. Okay, so that's the formal framework. So let's use this methodology, use this formal framework to develop a notion of social choice theory for countable societies. And when you do that, it turns out there are really two principal challenges. The first is cardinality. So if you've got an infinite set of voters and you have arrow's unrestricted domain condition, then you're going to have an uncountable set of coalitions, right? And this won't work in second order arithmetic because it's expressively very limited. You can't talk about uncountable sets. You can only talk about sets of natural numbers, all of which are countable. So that's one problem. And of course, the social welfare functions are also going to be uncountable objects, and thus, at least prima facie, they're not going to be candidates for the kind of thing that could even be computable in principle. So we need to find a way to cut this down somehow. In particular, we need to find a way to relax this unrestricted domain condition. But presumably we want to do it in a way that allows us to still prove Arrow's theorem in the finite case. Right? We don't want to relax it in a way that means that Fishburne's possibility theorem is trivially true. We want it to be true in a kind of substantial way. So we need to make sure that, for example, Arrow's theorem is still true in this setting. And the second challenge is effectiveness. So roughly here, the idea is just we're working in this base theory that only admits the existence of computable things, only has a limited amount of induction, and so we need to have definitions that are tractable within this weak theory. Okay, so how do we do it then? Well, voters, that's easy. Just take some infinite or possibly even finite set V of natural numbers. So the natural numbers are just being used to label our voters. We label them 0, 1, 2, etc. In the finite case, we'll only have finitely many. In the infinite case, it could be all of the natural numbers, or it could just be an infinite subset. So, we could just have the odd numbers, or the even numbers, or the prime numbers. Doesn't matter. And then the alternatives will just be a finite set of natural numbers. So alternative 0, alternative 1, alternative 2, and so on, as long as you've got at least 3. And W, again, will be the set of all weak orders on X. And in this setting, you have to do some coding so that you can represent these weak orders, which themselves will be finite objects, right? Because they're just like an ordering of some finite set of alternatives. So it turns out that we can code these up also by natural numbers. Okay, so then we have to actually start doing some work and address this cardinality issue by weakening the unrestricted domain condition. So we are only going to look at societies with countable sets of profiles. So that's already one big weakening of Arrow's conditions. And in fact, we're going to code them up as sequences. So you'll have some countable sequence of profiles, which can then itself be coded as a single set because of arithmetic. And again, with our algebra of coalitions, we're going to restrict from the algebra of all sets of subsets of our set of voters to some countable algebra. So it's going to contain the empty set, it's going to contain the set of all voters, it's going to be closed under unions, closed under intersections, closed under relative complements. But we don't put any other restrictions on. Except that it's also going to contain all singletons. And this is important because we want to make sure that the social welfare function has the possibility of being dictatorial. And if you don't have any singletons, you can't get that. This kind of move was already anticipated in the 80s by Thomas Armstrong. He generalized Kerman and Sondermann's results to algebras of coalitions. Okay, so we've got voters, alternatives, weak orderings. On those alternatives, we've got countable sequences of profiles, and we've got countable algebras also coded as sequences. But then once we've got this, not every such collection will determine a society, because we need to impose some further conditions. So we have a kind of problem of richness. We need to make sure that the algebra and the set of profiles, mostly the set of profiles, are sufficiently rich to allow the proofs to go through. And in particular, they need to be sufficiently closely related to one another. So Armstrong's solution was to just say, okay, I'm going to take some arbitrary algebra, and then I'm going to take all of the profiles that are measurable by some set in that algebra. But this doesn't work very well in a more effective setting, because it turns out that being measurable is itself kind of complicated as a property. So we need to assume that we have something stronger kind of baked into our society, namely that for every profile, it's going to be measurable via some uniformizing function. So here's the definition. Suppose we've got a non-empty set of voters and a finite set of alternatives, a countable algebra of sets, and a countable sequence of profiles. Then we say that f is uniformly a measurable via theta if theta is a function from indexes of profiles. So that every profile, they're coded in a sequence, they're going to have an index. Think of it as the name of the profile. And pairs of alternatives, x and y. And the idea is, okay, you give me the index of a profile, all right, some election, and a pair of alternatives for that election, and then I hand you back the index of the coalition of voters who prefer x to y. That's all there is to it. Okay, so that's one condition. The other side of this richness problem is that the set of profiles needs to be sufficiently combinatorially rich with respect to the set of coalitions. And in particular, and in some sense this is just to make proofs go through, our set F needs to contain profiles that encode membership, not just in individual coalitions, but in finite sequences of coalitions, finite partitions of V, in fact. In fact, they don't need to be very large, at least for the proofs related to Arrow's theorem to go through. You need like partitions of length 4 or something. In other contexts, you might need more, but for this, it's really pretty straightforward. So here's this definition. It's a kind of horrible definition. So don't worry too much about trying to follow the details. Roughly, the idea is that if we have any sequence of indexes of coalitions, then what we need is for there to exist a single profile that will give us back different weak orderings depending on whether the voter is in a particular one of the coalitions we started with. So here's the definition. Roughly, yeah, I guess usually I do this with a board, but okay, so imagine that we have, this room as the set of voters, and this is going to be coalition 1, coalition 2, coalition 3. And this quasi-partition embedding condition is going to say something like, okay, there's going to exist for any 3 weak orders a profile in which this coalition has weak order 1, this coalition has weak order 2, and this coalition has weak order 3. So for any 3. So obviously we're going to have several different profiles depending on how we choose those weak orderings. Okay, that's the essential idea. And this just ensures that F is rich enough that these proofs will go through. Okay, so that was the hard bit. And combining these definitions, we finally have the definition of a society. So a society, a countable society, is just a set of voters, a set of natural numbers, a finite set of alternatives, an atomic countable algebra of coalitions, and a countable sequence of profiles such that these two conditions are satisfied. One, F is uniformly A measurable, and two, A is quasi-partition embedded into F. And then we just say a countable society is finite if the set of voters is finite, and otherwise it's infinite. So far so straightforward. Okay. So in some sense, this is where all the real work is in getting the right definition. And this is true of a lot of reverse mathematics. Okay. So from this point on, things get easier. So suppose we have a countable society, then a social welfare function is going to be a function from natural numbers to weak orders. Why from natural numbers? Before we had the social welfare function was a function from profiles. Well, here the social welfare function is going to map indexes of profiles, right? The names of profiles, rather than the sets themselves. Okay? And it's going to need to satisfy the following conditions. This is just unanimity, formalized. This is just independence. And then it's non-dictatorial if it satisfies the non-dictatoriality condition as appropriately expressed within this framework. But really these just look exactly like the arrow conditions once it's all formalized. Okay, so then we can formalize our three statements as follows. So the Kerman-Sondermann theorem for countable societies just says, okay, if you've got a countable society and a social welfare function for that society, and from now on we always consider social welfare functions that satisfy unanimity and independence, then the set of sigma decisive coalitions exists, and it forms an ultrafilter on the algebra of coalitions, and it's principal if and only if the social welfare function is dictatorial. Okay. Arrow's theorem just says, well, if you've got a finite society and a social welfare function for that society, then it's dictatorial. And then finally, Fishburne's possibility theorem for countable societies just says, well, if you have a countably infinite society, then there's a non-dictatorial social welfare function, sigma 4s. Right? So in some sense, having done all of this work, we've packaged it all up in the notion of countable society. And the statements of the theorems are simple and just mirror those that we find in the classical social choice literature. Okay, so I said that a kind of adequacy condition on this whole enterprise was that we could prove Arrow's theorem in this setting. Otherwise, maybe we're just going to get Fishburne's theorem for free, and it's not really a good modeling of the original classical mathematical results. So let's prove Arrow's theorem. Okay, so an almost decisive coalition is one that is, in some sense, strictly decisive. So if we divide the set of voters into two, perhaps the people on this side of the room and the people on this side of the room, and all of you over here prefer x to y, and all of you over here prefer y to x, strictly, then this coalition is almost sigma decisive if your preference prevails. In these scenarios where we can exactly divide the set of voters in two, as those who have a strict preference one way and a strict preference the other way. Okay? There's nobody havering in the middle saying, oh, I'm not sure, maybe X, maybe Y. Okay. And we then get this kind of version of a classical result. It's called various things in the literature, like the contagion lemma or the spread of decisiveness. So suppose we've got a countable society, then the following conditions on a coalition are equivalent. It's decisive, it's almost decisive, it's almost decisive at a single profile, and finally, it's almost decisive at this one particular profile that we can compute. So it's like 4 is just giving us a computable witness for 3. Okay. And this is really the heart of the proof. It's the heart of Kerman and Sondermann's proof of Arrow's theorem and of their theorem. And it also allows us to prove the Kerman-Sondermann theorem in RCA 0, because if you look at this, you'd see that condition 4 doesn't have any quantifiers in. So we can prove that the set of indexes for coalitions that satisfy this condition exists in RCA 0. So this lets us prove the Kerman-Sondermann theorem in RCA 0. And because all of the ultrafilters on a finite set are principal, they're all generated by a single element. And you can prove this in RCA 0, just requires a bit of induction. Then we have the following corollary, that Arrow's theorem is provable in RCA 0, which is what we wanted. So far, so good. Okay, so this puts us in a position to look at this Fishburne possibility theorem and its non-constructive status, and finally get some kind of answers about that. So here's the result. So the following statements are equivalent over RCA 0, and I'm going to give a number of them just for illustrative purposes. But only the first one and the last one are in some sense essential. So Fishburne's possibility theorem for countable societies is equivalent to all of the following. Firstly, the statement that for every countable atomic algebra A over an infinite set V, there exists a non-principal ultrafilter U on A. So this is important because, of course, it shows us that, in some sense, non-principal ultrafilters are essential to proving Fishburne's possibility theorem. So we had them in this setting in set theory where they were these very complex, big, non-constructive objects. Down here in the countable world, they're much less complex, but they're still essential for proving this result. The third one in the list is that for every set X, the Turing jump of X exists. I'll explain what this means in a sec, but roughly it means the halting problem relativized to X. So a non-computable set, a kind of canonical non-computable set. And finally, arithmetical comprehension. So we have an equivalence to one of these big 5 subsystems of second order arithmetic. Okay, so yeah, the Turing jump of a set X, or X jump with the little tick, that's just the halting problem for Turing machines with Oracle X. So you have some enumeration of all of your Turing machines, and they can appeal to this set X, whatever it is. And then there's a question, well, do they halt or not when given their own index as an input? And if you assume RCA 0 and Fishburne's possibility theorem, then you can prove that whatever set X you have, the jump of that set exists. So you can always prove that these non-computable sets exist. So this shows that really Fishburne's possibility theorem not only relies on ultrafilters, but is essentially non-constructive in the sense that it relies on and implies the existence of non-computable sets. Okay, and maybe we'll just skip the actual proofs of these. Okay, and maybe I'll just pause at this point and wrap up. So we started with this question about whether there are non-dictatorial social welfare functions that correspond to rules, so ones we can compute. The answer is actually yes, but only when the algebra is very impoverished. So if you have an extremely simple algebra of coalitions, it's possible to have a computable but non-dictatorial social welfare function. But it does have to be very simple indeed. And in particular, it can't contain a set of this form. I won't explain in too much detail, but roughly just says that it's like a maybe I won't go into too much detail on this. We can cover it in the questions if people are interested. But this equivalence between Fishburne's possibility theorem and arithmetical comprehension shows that, in general, the answer to this question is no. We can't have social welfare functions that we can compute that are non-dictatorial. And then the second question was, well, are non-constructive axioms like the axiom of choice necessary to prove Fishburne's possibility theorem? And here the answer is, well, if we only look at countable societies, such as those we might use in intergenerational social choice theory, population ethics, this kind of thing, then much weaker axioms are in fact sufficient. So ACA 0, this is not just provable in ZF, it's far, far weaker. It's conservative over first order PA. So at least if we look at some restricted range of scenarios, no, you don't need some incredibly powerful axiom to prove the existence of these things. But nonetheless, it's still non-constructive. It still involves non-computability because it guarantees the existence of non-computable sets like the Turing jump. Okay, so maybe I'll stop there. Thank you.
Thank you very much, Benedict. There are immediately some questions.
Yes, thank you. I don't really understand the meaning you put to this or the goal you want to achieve, because I see that you have some nice mathematical results, but are you really looking for a way to implement like what a democratic decision making system would look like? Because I feel like from the beginning, you define, like, for instance, a dictatorial system where someone is always satisfied. But in fact, I could vote completely randomly and be extremely lucky, but we wouldn't call this dictatorship. So, for instance, when you put a citation at the beginning, it was said that democracy and fairness was not compatible, but I don't feel like it was the conceptual definition of democracy and dictatorship. And even though you could achieve to find a computable function, I would feel like it would be more democratic to have something that we could understand than an obscure NP-complete algorithm that no one can understand.
Yeah, so in fact, I share your concerns about the interpretation of the non-dictatoriality axiom. I mean, I think one way of thinking about it is that the point is that there will always be a dictator, in the sense that even if you vote randomly and you turn out to be the dictator in that particular society for that social welfare function, the point is that no matter what social welfare function is chosen, there will always be somebody who, perhaps through dint of just voting in a random way or through dint of enforcing their will on the society, whatever it is, there's always going to be somebody who will always get their way. Obviously, in the mathematical framework, you can't have any kind of causal link between that person voting a certain way and the social welfare function having a certain output. I mean, that kind of thing just isn't there in the formalism, of course. But nonetheless, I think there is something to the name, just because it's that for all social welfare functions you get this result, this impossibility result, that there will always be somebody of this nature who whenever they prefer X to Y, the social preference is exactly the same. Yeah, so that's the first point. The second, I mean, yeah, I think this is all very idealized, and we should worry about the extent to which it's idealized. I suppose part of the point of some of the slides I had towards the beginning about different notions of infinite society that are considered in different bits of academic research in economics and philosophy and political science is that at least this is something that people are working on. I don't know if we should take it too seriously that, you know, there might be some, as you say, random NP complete function that will do this. I don't think this is something that's about to have any kind of application to elections in the immediate future. It's more, I suppose, in the vein of a sort of normative project, right? In the sense that, I mean, when I have my philosopher hat on, I think of it like this. We want to think about possibility in a fairly broad sense. It seems like computability, it gives us a quite clear demarcation between things that could, in principle, if given access to sufficient computational resources, be carried out, you know, thought processes or decision mechanisms that could be carried out, versus those that can't be. And so we have this kind of bright dividing line. And there's a strength to the results in that sense, right? So if we show that something is non-computable, then we show in a certain sense that it's impossible, modulo any kind of discussion about hypercomputation, etc. And then, you know, if it's possible, then I agree that there's a big discussion to be had about whether it's feasible and whether it's open to some kind of introspection, etc. And that's all perfectly reasonable. I agree completely with that. But I think the value of these kinds of results is just that, you know, they contribute to this kind of more general question about possibility, not necessarily in, you know, something that's going to be implemented by us, but you know, can in general be possible or not be possible. So I'm not sure that really answers your question, but I'm very sympathetic to the point.
We have a question by Jérôme.
Yes, a quick question. So when you gave motivations about justifying infinite societies of voters, I mean, so there was one motivation with the future generations, and another one with the states of nature. And this I did not. Okay, so I see that you have an infinite set of states of nature, but then if you apply a social choice mechanism to that, I mean, you're going to output a pair consisting of an alternative and a state of nature, but you cannot choose states of nature. So how do you cope with that?
I mean, the output is just going to be a weak ordering of the alternatives, right? It's not going to have the state in it. That example comes from this paper by Mihara, and he talks about various scenarios like where we have experts recommending the adoption or not of various drugs, this kind of thing, depending on whether or not certain conditions are met. I'm not sure that in that specific example I find it super plausible that there are going to be infinitely many outcomes, but infinitely many states that we might want to index on, but maybe we can come up with some more natural example along those lines. Yeah.
Maybe we should stop here, have a break, and think again. Oh, you had the question, Walt.
Yes. So, okay. There's also, of course, all of these famous results about manipulability and strategy proofness of voting systems, and impossibility results like the Gibbard-Satterthwaite theorem, which kind of corresponds to Arrow's theorem in that setting. These results also have possibility theorems in the infinite case, and you can do a similar kind of analysis there and get pretty similar results, a similar kind of equivalence to arithmetical comprehension. So I don't know if that's what you wanted, but okay. Yes, so hence non-constructive, non-computable, etc. Yeah.
Thank you again, Benedict.